Okay, welcome to Chapter 4. We're going to be discussing Newton's law of motion, and that's going to revolve around the concept of force. The reason we have been studying vectors up to this point is not only for velocity, for acceleration, but it's going to tie into something that is bigger conceptually than just those concepts. Force is going to be a vector quantity. It's going to be a quantitative measure for the mechanical interaction between two objects. So when several forces act on an object, the effect is the same as when a single force equal to the vector sum or resultant of the forces acts on the object. So you can see here in this particular picture, two forces acting on a point have the same effect as a single force R equal to their vector sum. So in other words, if you added this force and you added that force, this is the resultant. Everything's going to act as if it's just got this one force being acted on it. And the great thing about that is that you can take that one vector and you can make it into components, an f, y, and an f of x, where you have components of that one vector being pulled in those directions. So, force is going to be defined as a push or a pull on an object. It's an interaction between two objects or between an object and its environment. A force is, of course, as we discussed, a vector quantity. It's got both magnitude as well as direction. So this would be an example of a push, obviously. This is an example of a pull. And gravity is an example of a force that acts over a distance. So when a force involves direct contact between two objects, it's called a contact force. When an object rests on a surface, there's always a component of the force perpendicular to the surface. And we're going to call that component a normal force. And normal here means that the force is always pointing away from the surface. It's another way to think of it is perpendicular. Normal is another way of saying perpendicular. There may be a component of the force parallel to the surface running this way. That is going to be called a friction force, and that's going to resist the sliding of an object on the surface. So when a rope or cord is attached to an object and pulled, the corresponding force is going to be referred to as a tension force. So we've got a normal force here. You can see it's perpendicular to the surface, both there and there. The surface exerts a push on it that is directly perpendicular. Friction force, in addition to the normal force, the surface may exert a frictional force. You've got a tension where the pulling force is exerted on an object by a rope or cord. And then you've got weight, the pull of gravity on the object. So how to measure a force? That quantity is going to tell us how strongly that force pushes or pulls. The SI unit for the magnitude of force is going to be called the Newton. The weight of a medium-sized apple, if you want a general sense of it, is about 1 Newton. The pulling force of a diesel locomotive can be as great as 10 to the 6th newtons. So, because an ideal spring will stretch or compress from its equilibrium position by an amount that's proportional to the force applied to it, we can use that spring to measure the magnitude of the force. So in other words, a coil spring will stretch or compress when a force acts on it. And this property forms the basis for a common unit called a spring balance. And you can kind of see that here. This is the device that's going to be used to kind of measure what that force is going to be. So you've got a 10 Newton force pull that's directed 30 degrees above the horizontal. You've got a 10 Newton push directed 45 degrees above the horizontal. You can see that this is pulling it, so that's why the direction of the vector is that way. This is pushing on the object, so that's why the direction is that way. So we're going to discuss here the superposition of forces. So as I had discussed before, if you've got a force this way and a force that way on an object, if you add the two together, you end up with a resultant. That resultant is the same as just having one force push on the object that way. And this is called the superposition of forces. So any force can be represented by its components acting on the same point. So let's say we've got that resultant vector here. We can represent this vector by this vector as well as that vector. If we break it down to its components, it'll be the y and the x direction. So again, you can see the picture here. The force in the y direction is the same as somebody pulling it up. The force in the x direction is the same as somebody pulling it this way. If we just had those two forces, that would be the same as this. So another example, let's say we've got a stonemason who is pulling on a block, force is pulling up that way. Then there's a component of that force pulling in this direction, and then there's a component that's also going in this direction. If we're going to look at the superposition of forces concept again, where the resultant is the sum of all of those forces, we can also look at the components of each vector and say that the resultant in the x direction is the sum of all forces in the x direction, the same thing for the y. And the resultant overall, its magnitude, if we're looking in just two directions, is going to be follow the Pythagorean theorem, and it's going to be the square root of the rx squared plus the ry squared. The tangent of the angle that's created with the horizontal is going to be r sub y divided by r sub x. Again, this is going to be measured counterclockwise from the x-axis.